Alright, I hope this video isn't too late for you guys. I got a lot of requests about how to tell which kinds of hypothesis tests to use, and I know we're like a couple of days away from the AP exam, but hopefully you'll find this a little bit helpful to explain how do you decide which hypothesis test to do, which is one of the key cornerstones. And we're also going to go through each test as well as the conditions and why the conditions are the way they are, okay? And yeah, so let's just talk about this. First, you have the way I decide what tests to do is really the kind of sampling that you're doing in the experiment, you either have one sample mean, one proportion, or you have two means and two proportions, right? That's really only the four categories you're gonna, because you don't have chi-square tests this year. So you either have one sample, you have one mean, you have one proportion, you have two means, or you have two proportion. Now, what's the difference between a proportion and a mean? Oops, sorry, I was cutting off. Let me rewrite that. So I was saying you have one mean, one proportion, two mean, or two proportion. Now, what's the difference between a proportion and a mean? A proportion is a binary. It's a categorical variable. It's like the percentage. It's always a percentage. It's like the percentage of people who wear seatbelts, the percentage of people who smoke, the percentage of people who are Democrats, that kind of thing. It's a proportion out of a total. And so that when you're measuring like a percentage, you're talking about a proportion. That's how you distinguish between a mean and a proportion. The mean is like some numerical value that's not a percentage typically. It can be a percentage, but it's more about like it represents some quantity. So it could be like the number of seeds in an apple, or it could be the number of ounces that are in a water bottle, or it's a measurement of some kind of substance. It's usually an amount of something, but it's typically a quantitative variable. Okay, for the mean, it's a quantitative, and for proportion, while it's a percentage, usually it's like you say you have 30 out of 80 people say they like pizza. That's abysmally low, but you get the idea, right? Like 30 out of 80 like pizza. This is a categorical variable, not a quantitative variable, but we convert it to a numerical value by saying 30 over 80, okay? Now, each of these, so when you talk about means, your sample values, like whenever you have a mean, your statistics or some of the variables you use are going to be like x bar, mu, and when you're doing proportions, they look like p hat or p. Sometimes you'll see p0. Sometimes it just depends on what you're talking about there. But that's the general idea, the difference between the variables between means and proportions. Okay, so that's the first thing you have to decide. Are we doing it with means or proportions? Hopefully the two amount of them makes sense. Like you're either collecting one sample or you're doing two of them. You either have two proportions or one proportion, or you have two means or you have one mean. And so that's how you distinguish all of those. Now let's talk about what a one sample mean. Let's talk about let's go one at a time. So suppose now I've narrowed it down. I have a one sample mean. Okay, so I'm measuring some kind of mean value, and it's a sample, and it's only one sample. The first question you have to ask yourself is whether or not I use the z or the t distribution. Okay, so now we're down to a one sample mean, and you have to decide, do I do a z versus a t? Now, when do I use a z distribution? The z test you would use when the population standard deviation is known. Not the sample standard deviation, okay? The population standard deviation. That means I know what sigma is. Sigma represents the standard deviation of the population, right? That means of the entire thing. So if I were to say collect the average height, if I were trying to figure out the distribution of the height of people in America, what's the average height? Okay, the standard deviation would be if I collected the entire U.S. population, measured their height, and calculated the standard deviation. That would be the population standard deviation, as opposed to if I just selected like 30 people and measured their height and grabbed that standard deviation. That would be my sample standard deviation. So you usually have the sample standard deviation, and you usually don't have the population standard deviation. So Z is less common to use for a one sample. But if you do have the standard deviation, technically you're supposed to use the Z test for the one sample mean. Okay? So that is if the population standard deviation is known. The other case is also weird, is like you might do the Z, or, this is a big or, by the central. So one of the things that we have that's very powerful is the central limit theorem. And the central limit theorem says that as long as the sample size is large enough, it is going to look normal. So there are various rules of thumb, but as long as n is large, say like in the old days it was about 30, but sometimes if you had like 50 or 100, something like that, when n is large enough, that is sufficient to say like, oh, I can use the normal distribution because the sampling distribution will look about normal anyway. Okay? So that's with that case. So the opposite case is when you use the t distribution. The t distribution is when you don't know sigma, the population standard deviation. And the sample size is relatively small. There are some rules of thumb, like I said, about less than 30 or so, we would say about is relatively small. Honestly, I don't think they usually don't stray into what about 30, what about 35? Like at that point it's a judgment call. Basically, Z is an approximation. Normal is always approximation if you don't know the population standard deviation. But when n is large enough, the t distribution looks a lot like the normal distribution. Like if I do n of like 1,000 and you ran a t test versus a Z test, you would find virtually no difference. Okay? And so that's why when n is large enough, it doesn't really matter which one you do because the t distribution ends up looking like the normal distribution anyway. And so, like, there's a slight error, but not very much. So, typically, you use the t if the sample size is pretty small. We're talking about the order of, like, 10 to 15 or so is, like, is common in a question. Could be less, maybe more like, maybe up to 20. But once you get around to 30, 40, 50, 100, it's okay to use the Z distribution, even if you don't know the population standard deviation. That's why I find, most people find this very confusing, which one to use Z versus T. But hopefully I've cleared it up as to how you're going to choose between Z versus the T. And T, you're going to use the degrees of freedom equals n minus 1. That's where T distribution has the degrees of freedom business. Okay, let's look at the conditions. If I'm going to do a one sample mean with a Z distribution, you're going to have to find, there's usually, there's 3 conditions that you typically have to obey when you're doing these tests. One is that a normal distribution is appropriate. That means so that means the way you know a normal distribution is appropriate is either you know the population is distributed normally, or or the sample size is greater than or equal to 30. Right? That's, we talked about the Z versus T, but that's technically saying that, okay, I know it's normally, because the central limit theorem says if I sample a large enough sample size, that the sampling distribution is going to look approximately normal. So that's the first condition usually for all the distributions is about normality. The second condition has to do about independence. Now, independence, you have to go back to your when you're doing probability with or without replacement. But independence has to do with the fact that if I do with replacement, when I'm drawing something out of a bag and I do it with replacement, it's independent. Whereas if I do it without replacement, it's not independent. And when you're sampling, you're never sampling the same person over and over. So technically, you're doing it without replacement. But if your group size is so large that it's very unlikely for you to draw the same person twice, then we say that it's pretty much as though it were without replacement. Technically, when you sample, it is without replacement, so they're not technically independent, but we can say it's approximately independent as long as the sample size is less than or equal to 10% of the population. That's saying then, even though I'm doing with replacement, that it's close enough. It's reasonable enough because the pool is so large that it's unlikely you're going to get. But if my sample size is close to the size of the population, then the fact that I'm doing it without replacement makes a big difference, and we cannot assume independence anymore. Okay, so independence is the second criteria. The third is that it's random, and this just indicates that the sampling has to be done randomly. There's no bias in the selection. And so those are the three conditions that you usually have to outline and explain before you use the test of inference test, okay, for the one sample mean z. Now, if I do the one sample mean with the t distribution, what do I have to do the condition? Well, my normality condition is that the sampling distribution is about normal. Because remember, is approximately normal. Normal, that means no skew and no outliers. So as long as, if I were to take, see, the one thing about the normality condition for t-test is really that I don't know anything about the population, so I can't assume that the population, and again, because the sample size is very small, I can't use central limit theorem to tell me that it's a normal distribution. So I have to, as long as the distribution, you look at the data, it looks about normal, it's not skewed one way or the other, then you could say, well, the distribution looks about normal, so we'll just assume normality there. The independence and the random are the exact same. So same independence and random as the one sample mean for z. So same conditions there. Sample size must be less than or equal to 10% of the population. Okay, so that takes care of the one sample mean scenario. Now we move on to the one proportion, one sample proportion or one proportion. And the reason we do this is z. It's never a t distribution with proportions. And I want to explain why you do it that way. It's because when you're doing proportions and you're doing a yes-no or a binary outcome, really what you're doing is you're doing a binomial distribution. Like if I sampled 100 people and I just randomly say yes or no question, like 1 or 2, and I calculate the proportion, that's really a binomial distribution because there's 2 outcomes and a fixed number of trials. Okay. Now, what is the standard deviation of a binomial distribution? It's the square root of p, 1 minus p over n. Okay. So here's the thing. If I know the proportion, I know the standard deviation of the population. See that? That's what this formula tells you when you're doing the standard deviation of a binomial. Remember, this is a binomial distribution. If I know the p, that is the proportion of the population, I automatically know the standard deviation. And remember what I said about when do I use t is if I don't know the population standard deviation. But because of my sample, if I know the sample proportion that I assume is equal, which in a sampling distribution would be equal to the population proportion, then I already know the population standard deviation by that formula. Thus, I always use z. That's why there's no one prop t test. It's a one prop z test only, because you always know the standard deviation. Okay, what are the conditions that we're going to use? Again, so there's nothing to tell. Once you know it's one proportion, you automatically use a z test. What about normality? In order to use remember, so this is a binomial distribution. In order to know that it's normally distributed, is there's an assumption about the normal approximation to the binomial distribution. And that only occurs when n times p is greater than or equal to 10, or n times 1 minus p is greater than or equal to 10. Some books do 15. I think for the AP exam, they pretty much say 10, but it's a little arbitrary. They say as long as there's enough successes and failures that the binomial distribution is going to look kind of like a normal distribution. That's kind of one of the early things maybe you learned in statistics. Maybe you didn't, but now I'm explaining it to you. That from the binomial distribution, you can approximate as a normal as long as those conditions are met. So that's the normality condition. The independence condition is the same as long as the sample size is less than or equal to 10% of the population. Again, that has to do with the with replacement, without replacement kind of business we just talked about. And then 3, it must be random. Okay? So a lot of these conditions overlap quite a bit. But just keep in mind that the normality condition is the one that probably changes the most among the different tests. So keep that in mind, what the normality condition applies for which test and why that matters. Okay, I think in one of the sample questions for the AP Statistics this year that the College Board did, I did a video on it. They talked about why this condition matters, and it's the normality condition. It's the normal approximation to the binomial distribution that you care about. Okay, so that's the one prop stuff. Now let's go into the two. So that's one. If I have one, either I have a one mean or a one proportion. Those are the tests. If I have a two mean, let's look at the two means. I have two scenarios I need to worry about, whether it's independent or not. Independent versus dependent. Okay. That means whether the two samples are related to one another. Okay. So one example of a dependent set is if I measured my weight today, and then I measured my weight, or I took a group of people, I took 10 people, I measured their weight, and then I measured their weight in like 6 months. And then I wanted to know if there was a difference. They're dependent because it's the same group of people. There's a relationship between the two samples. Even though I have two sets of data, they're related to one another. So if it's dependent in some way, we're typically going to use the matched pairs test. Matched pairs is a pretty simple test. I mean, it sounds complicated, or it sounds like a new thing. But what you do is you would measure the differences and then run a one sample test on it, on the differences. You're going to run a one sample on just the differences. You're really saying there are not really two samples. There's only one sample, and the sample is the difference between the two samples. Does that make sense? Of the individual samples. So as an example, let's do my weight example. Let's say someone was weighing 110, one was 130, and one was 120. And then this is person A, this is person B, this is person C. And then later on, they measured 115, 125, 140. Okay? So this is now. This is in 6 months. And then what you would do instead is you would take the difference of the individual samples and say this is a positive 5. It doesn't matter which direction you do it in as long as you're consistent. So I'm going to do now minus 6. Or we'll do 6 months minus that minus that minus that, minus 5, that minus that is 20. And then I would run my test on this data instead, okay? But as a one sample. So if it's dependent, you really turn it into a one sample and then run a one sample test on it. And again, your inferences are pretty much the same as before. Normality, that either the sample sizes are large enough to assume it. In these cases, you almost always do a t-test because unless the sample sizes are very large, you could still do a decision between t versus z. And again, you can use the same decision making. If the sample size is large enough, you could say, well, the normal distribution looks about the same as the t distribution, so I can use a z-test, and the answer won't be very different. You can also use a t-test. T-tests are more common because usually when they ask these questions, they're small sample sizes, so they're not very large. And so you can't, use that assumption. And you typically don't know the population standard deviations of both sets of data. So that's why you typically don't see a z-test when you're doing two mean. Although technically you could do a z-test as long as it met the conditions for a z-test. Okay. But everything else is the same. Normality, independence, randomness. Those three conditions about the same as the one sample. If they're independent, that's when we run the that's when you're looking at the difference between the two means. That means you're going to look at like x1 bar minus x2 bar, and you're going to look at mu1 minus mu2, like that kind of thing. Like you're going to run the difference of the sampling distributions, okay? And we call this a two-sample on your calculator. Let me pull up the calculator just so we can kind of see what it looks like on your calculator. On the distributions, oops, let me turn it on. Oh, no, sorry, not the distributions, the tests. You would do a two-sample Z or T, probably T. Like I said, T is more common. That is when you have two independent. You're going to run a two-sample test, okay? Whereas remember, if they're two dependent samples, you're just gonna run a one sample Z, or you're gonna pick Z or T. They didn't write one sample, but like implicit in 1 and 2 is the fact that it's one sample. Okay. Any special conditions on the normality? Let's see. Normality conditions about the same, just that the distributions look about normal. The sampling distributions look about normal. The randomness. Because they're independent, the two samples must be randomly selected from each other. It's like there can't be any relationship, no dependency between the two samples that you're selecting from. So if they're independent, not only does it be random, but it has to be kind of like, independent and separate. Like the two samples are not connected in any way. They're random in some sense. Okay. Let's see. And then finally we have two prop test, which is always Z, like we just talked about. Yeah, we talked about it always being a Z test, because once you know the population, or your sampling distribution mean is going to match the populations, and once you know that, then you know the standard deviation of the population, and hence you're going to use the Z test. Okay, so there's no T test. That's why you see the one prop Z, one prop, two prop Z, but no one prop T. Okay, you never do that. The conditions are pretty much the same for this one. For normality, we still want to use the binomial approximation to a normal distribution, but that it needs to be held for each sample. That means n1 p1 has to be greater than or equal to 10, n1 1 minus p1 is greater than or equal to 10, and then for the second sample too, it has to be held, because I need both samples to be normally distributed, the proportions at least. The independence is the same. You can't draw more than 10% of the population. That's pretty much exactly the same. And then random is that basically each sample is randomly selected, as well as the two proportions, the groups that you sampled from. There's no connection between them either. Okay, so those are the major conditions. And then that pretty much covers all of the tests. I mean, there's some formulas related there. I think you can look up the formulas, but hopefully at least that clears up the gist of how you decide which test to use and which calculations to run, which one on your calculator to run.